Hello everyone, we're the group that's doing the pulse oximeter. I'm Raphael.
I'm Alanis.
Sepehr.
And here we go. As for the motivation as to why we were studying the pulse oximeter, anesthesiology is very important for studying the levels of, or for keeping patients calm while we're doing operations on them. And it's very important to keep all of their chemical levels stable. So a certain condition called anoxemia is when a certain patient has oxygen levels in their blood underneath a normal level and could potentially put them at risk. The pulse oximeter is a tool that we use to measure when a patient reaches anoxemic levels. Now, for a brief history, the first few oximeters, they weren't even pulse oximeters, were developed in around the 1940s by a man named Millikan. And they're basically an attachment to the ear where they use two wavelengths of light, one sensitive to changes in oxygen concentration in the blood, one that wasn't, so that we could use it as a base for comparison. These oximeters were useful, but they weren't exactly well marketed because they were bulky. They had the potential to burn their patient because they used heat to arterialize the blood, that is to enhance the amount of oxygen in it. And they were very hard to calibrate. You had to recalibrate it every single time you used it on new patients. It wasn't until about the 70s when an engineer of the Nihon Koden Corporation added the idea of looking at the pulsatile flow in the blood. And from there, the first pulse oximeter was developed, but it didn't really sell well. However, in the late 70s to early 80s, someone from the Black Corporation in Colorado made a few adjustments to pulse oximeter, which made it a little bit better. They added LEDs so as a light source and photodiodes as a receptor. And they also added a digital microprocessor, which held an algorithm for calibrating the machine. And now Jose will give you a little bit more on other details.
Okay, so some of the common uses for the pulse oximeter were, as Raphael mentioned, for anesthesia. So when you're like in the intensive care operating room, anesthesia is shutting down your body, so you need a ventilator in order to keep you alive, right? You need certain oxygen levels. And so the pulse oximeter will tell you what's the oxygen concentration that you have, so they can adjust the ventilator in such a way that you can survive. And in addition, it can also determine cardiac and respiratory diseases, and most notably the chronic obstructive pulmonary disease and sleep apnea. And so for you guys to understand a little bit about the COPD, here's a quick image of the respiratory system. So you have the trachea, then branches off into bronchus, then the bronchioles branches off more, and then eventually gets to alveoli, which there's oxygen diffusion into your blood. All right, so some types of chronic obstructive pulmonary disease are emphysema, chronic bronchitis, and Okay, so emphysema deals with inflammation and obstruction of the bronchioles. So then this causes the alveoli to be sealed off, and then those will get inflamed. And as you breathe, there's changes in the pressure, and eventually alveoli will start bursting. And so you can see you'll have an image like that. So they get inflamed, and then you're starting to lose alveoli. So surface area decreases, so oxygen levels, you can't absorb as much oxygen as before. Then you also have chronic bronchitis, which basically is an obstruction. So let's say you're smoking, it irritates your bronchus, so your body creates mucus to defend itself, but then that same mucus blocks the airway. So then, again, so it's reducing your oxygen level. And then you have this other one, which basically is the same as this one, as chronic bronchitis, but that one just involves you smoke, irritates, you get mucus, and now bacteria such as Staphylococcus or another bacteria, which I can mention later. It goes into the mucus, and then it basically just keeps on irritating your lungs. And so, as to sleep apnea, you have obstructive sleep apnea, central sleep apnea, and complex sleep apnea. Complex sleep apnea is the combination of both of these, and obstructive sleep apnea basically deals with the soft tissue of your throat, the collapsible walls basically get in the way of your airflow. So then when you're breathing, this will basically close the airflow, and then you'd have trouble obtaining your oxygen. And for central sleep apnea, basically your body can't distinguish, doesn't have the right process control to distinguish the feedback, so it can't adjust itself to receive the right amount of oxygen. And so Sepehr will now talk about how it works.
So I'll talk about how the pulse oximeter works. But basically, it follows your law. You send in some sort of light, and based on distance, concentration, and extinction coefficient, you're going to get some light transmitted. As you can see here, these are the two who are most interested in reduced hemoglobin and oxyhemoglobin. And at 960 and 640, each of them have over here slightly, but over here a large difference in the extinction coefficient, which will change their transmitted light. So the two wavelengths used in most modern pulse oximeters are 660 nanometer and 940. To filter out noise and other stuff, they use they basically look at when the light hits, it looks at DC and AC signal. The AC is due to pulse output from the arteries. So it's going to be varying over time, while the venous flow and blood absorption due to tissue is going to stay constant. So you divide the changing absorption or the changing transmitted light by the DC signal.
Yep, 30 seconds left.
Okay, so you divide these and you get R. And R, the graph R, and this is based on experimental data from studies. So that's how you relate the two, and then you know how much the oxygen saturation of the blood's at. So some other techniques you have, there's variability in the wavelength of the LED. So one way would be to reject all the ones that are like 5 or 10 nanometers apart, but that's too expensive. So instead, they have software to allow them to adjust for these differences. Also the pulse oximeter can't differentiate between the lights coming back, so it shines one light, then it stops, and the other light, then the room light. And through this, it's able to distinguish which one's there. There's also a shield, so opaque shield, which does not allow light to go through. Other ways, the signal can be amplified if the signal is weak, up to a 4% baseline of the arterial blood flow. And patient motion also causes large disturbances, which is combated by algorithms which averages that up. So improvements on it, you can put a motion sensor or accelerometer to get rid of this. There's also a
Time's up. Let's move to